Hello and welcome to yet another video of Cornerstones of Math. Before we dive into today's problem, let me briefly introduce a bit of context. About a month ago, I released this video where I solved this problem. When theta equals 2 pi over n, where n is a natural number greater than or equal to 2, prove that cosine theta plus cosine 2 theta plus cosine 3 theta plus so on plus cosine n theta equals 0, and sine theta plus sine 2 theta plus sine 3 theta plus so on plus sine n theta equals 0. You can check the link to this video on the top right corner of this video. In that video, I have provided two different methods to prove the given identities. The first one was the geometric proof using vectors, and in the second method, I have provided more general version of the given identities using a whole bunch of trigonometric identities. But here, I want to show you the third method, the complex number method. So, how does this work? Well, first we start from seemingly unrelated problem, which is finding the roots of the equation z to the power of n equals 1. You see, since this is an nth degree polynomial equation, it must have n roots. In other words, this equation, equivalent to z to the power of n minus 1 equals 0, can be factored into z minus z1 times z minus z2 times z minus z3 times so on, all the way up to z minus zn equals 0, where these, z1, z2, z3, zn minus 1, zn, are roots of the given equation. And we can express these roots in a pretty neat way. It is known that the n roots of the equation z to the power of n equals 1, denoted as z1, z2, z3, so on, zn, are given as the first root z1 is cosine theta plus I sine theta, where theta is 2 pi divided by n, and I is the imaginary unit. And the second root z2 is cosine 2 theta plus I sine 2 theta, and the third root z3 is cosine 3 theta plus I sine 3 theta, and so on, up to zn, which is cosine n theta plus I sine n theta, and given this value of theta, this zn is just 1, the obvious root and the trivial root. In other words, the roots are given as zk, which is cosine 2k pi over n plus I sine 2k pi over n, where k can have integer values from 1 to n, or depending on the context, from 0 to n minus 1, which is essentially the same. But how can we guarantee that these are indeed roots of the given equation? We at least have to check, so let's quickly check. The checking process is quite simple. We simply raise every root to the power of n and check whether the result is 1. But in order to calculate this exponentiation, we require one fascinating theorem, known as de Moivre's theorem. The theorem states that for any real number x and integer n, cosine x plus I sine x raised to the power of n equals cosine nx plus I sine nx. Now I don't want to spend too much time on the proof because that's not the main focus of this video, so I will only briefly mention here that this theorem can be derived from the fact that if the two complex numbers of this type are multiplied, their angle parts are simply adding up. Using de Moivre's theorem, if we raise z1 to the power of n, which is this to the power of n, we simply obtain 1. Similarly, if we raise z2, z3, and zn to the power of n, we can also obtain 1. Thus, we have verified that z1, z2, so on, zn are all roots of the equation z to the power of n equals 1. Now, using de Moivre's theorem, let us do something different using this z1, cosine theta plus I sine theta. If we square z1, then by de Moivre's theorem, we obtain cosine 2 theta plus I sine 2 theta, which is z2. And if we cube z1, we obtain cosine 3 theta plus I sine 3 theta, which is z3. And you can go on and on until you obtain z1 to the power of n equals zn. Therefore, we can say that the n roots of the equation z to the power of n equals 1 are, instead of using z1, z2, z3, zn, we can say that they are z1, z1 squared, z1 cubed, and so on, all the way up to z1 to the power of n. Or since this z1 to the power of n is just 1, we can say they are 1, z1, z1 squared, and so on, all the way up to z1 to the power of n minus 1. Now these are all fascinating stuffs for sure, but still, our main goal is to prove these identities by somehow using stuffs I have explained so far. And for that, let us focus on only one root, this z1. Since this z1 is a root of the equation z to the power of n equals 1, we have z1 to the power of n minus 1 equals 0. Here, the left-hand side can be factored using the following factorization formula of x to the power of n minus 1. Since x equals 1 make the left-hand side 0, it has x minus 1 as a factor, and if we carry out the division, we eventually obtain this formula. So we have z1 minus 1 times, and if we write 1 first, we have 1 plus z1 squared plus so on, plus z1 to the power of n minus 1 equals 0. Here, z1 is obviously not equal to 1, so this part cannot be 0. This means that this equality holds not because z1 minus 1 is 0, but because this part is 0. So we have 1 plus z1 squared plus so on plus z1 to the power of n minus 1 equals 0. Or since this 1 can be written as z1 to the power of n, it is more convenient to use z1 plus z1 squared plus so on plus z1 to the power of n minus 1 plus z1 to the power of n equals 0. Here, this z1 is obviously cosine theta plus I sine theta, and this z1 squared is cosine 2 theta plus I sine 2 theta, as we have already shown using de Moivre's theorem, and so on, and this z1 to the power of n is cosine n theta plus sine n theta. So we have this. Here, if we write the real part and the imaginary part separately, we have this. Therefore, from the real part, we obtain cosine theta plus cosine 2 theta plus so on plus cosine n theta equals 0, and from the imaginary part, we obtain sine theta plus sine 2 theta plus so on plus sine n theta equals 0. And this completes the proof. So that was all for today's video. If you haven't seen my previous video using other methods to prove these identities, check out this video on the left, and if you're interested in this video, please check this video on the right where I explain 3 different methods to rotate a point or a vector, where one of them includes complex numbers. Also, please don't forget to hit the like and subscribe buttons, and I will see you in another video.